Suppose we have 36 people in a room and we want to find the probability that at least 2 of them share the same birthday. Now that probability wouldn't seem very high since that's less than 1/10 of all possible birthdays. But as we see that, if we look at this in the sense by looking at the complement first, what's the probability that no 2 people have the same birthday? Well, when there's one person, it's certain they're going to have the same birthday. But if I add a second person, for them to have a different birthday would be this product, a third person, assuming there's no leap years, all the way down to a 36th person. You notice the numerators are descending by 1. So if I said I have 36 people, my numerator would be the permutation, 365, choose 36. My denominator remained the same. This would be the probability that no 2 people share the same birthday. So the probability that at least 2 people share the same birthday would be the complement, which surprisingly is very, very large. Now the question is, how could I be absolutely certain? How could I guarantee that at least 2 people share the same birthday? Well, that's where the pigeonhole principle comes in. If there's 365 possible birthdays, then any group of people that are more than 365, at least 2 of them would have to share the same birthday. Now suppose we have a standard deck of 52 playing cards where there are 12 face cards, the jack, the queen, the king of the 4 available suits. I'm going to choose 10 cards at random simultaneously, so therefore without replacement, and I'd like to find the probability that at least 2 of them are face cards. So once again, let's start with the complement. Let's suppose that none of them are face cards. So the probability that I choose a card and it's not a face card would be 40 over 52. A second card, 39 over 51, a third card, and so on. If I do this and I'm going to choose exactly 10 cards, then I will end this at 31 over 43. That's exactly permutation 40 choose 10 over the permutation 52 choose 10. This is the probability of none of the 2 cards being face cards. So what we want is the complement of this. Which once again yields a very, very large value. In this case it would be 0.9464. We have almost a probability of 1 by just choosing 10 cards. So the question is, how many cards would we have to choose to guarantee that at least 2 of them are face cards? Well, we can see by looking at this, as I continue choosing cards, the only way we're going to get an answer of 1 is if the term on the right was equal to 0. The term on the right will equal 0 the moment the numerator hits 0. And it'll hit 0 on my 43rd choice. So again, according to the pigeonhole principle, if there are 40 cards that are not face cards, if I choose 41 cards, then at least 2 of them will have to be face cards.